Yeah. So, hey, Doug.
Hey, Doug.
Good morning.
So funny
Mathematicians.
that she posts her things that I've seen, Connor.
Cool phase planes. Can't wait to talk about that. Euler's method. And Connor showed up in video. What's going on, Connor? You never do that.
I know. I do it sometimes. I have to bail early at like 9:15 to go to a haircut. So I'm trying to make the most of my time here.
Well, cancel that appointment. Come over. I'll cut it for you.
I'll take you up on that offer if you're serious. Honestly, I hate paying for haircuts. That's why I let it get so long, and I do it like once every 3 months because I hate it.
Yeah.
That is not long.
I mean, David, your hair is pretty long. This is long for me.
Yeah, it's a tolerance. It's a tolerance thing. No, Landon even showed up. What's going on? Got some people on the screen today.
Now I have a face to look at when I scream for answers. Landon, help me!
Awesome. It's good to see you guys. What's how you holding up? It's the bitter end here. You know, somebody know in Calc 4, and it's like this is end of the second to last week. Man.
Yeah, I was going to ask you, is the last test going to be cumulative, or is it just going to be over what we're studying right now?
No, it's going to be cumulative, but over the main plane stuff. So I'm imagining it will feel like a breeze.
Yeah, I mean, it seems like we're kind of incorporating like everything in what we're doing right now. But I was just curious, like.
Yeah. Fortunately, this class kind of has a building sort of a feel to it, so it isn't just a whole bunch of different topics. Really, the entire time we've just been figuring out ways to solve differential equations. So, yeah, some truth in that. And then I'll have a few questions. This 5th chapter is kind of after the last, and also I can have a chapter test about that. So I'll have a little bit more of that in it, but yeah. Cool. Well, I want to show you something kind of neat. I hinted at this going out the door yesterday. And again, I intended to talk to you about the project today, or like, show you the answers to it, so to speak, the different ways to look at it, but I gave you guys an extra day. So I don't think what I'm going to show you today is going to take the entire time. So we should have some time to talk about the project if you have questions after that, if you like. But this is kind of neat, and I hope you'll agree. So 5.3, and I'll remind you of this because it's probably way in the back of your mind, but this is Euler's method, which was what we used way back at the start when we were trying to solve a differential equation before we had any techniques to do it. We just realized we could creep along the answer, and actually make the graph of the answer to the equation. And that at the time, though, was only first order. But now we're doing second order. And so at the time, and I'm going to explain this a little different than I did back at the time, just to give you kind of a bit of an explanation, kind of a better, maybe a simpler explanation of how it worked. But the basic idea last time, kind of whatever that chapter was kind of this. If we said, okay, there's your y of, let's say this is like 3 and that's 2. And so it's kind of like your initial condition, your initial starting point is at the point 3, 2. And so logically we said before, okay, if you're at the point 3, 2, and so you know where you started, and you also know the slope, like y prime of 3, we also know the slope there is say 1/2 or something like that, then it basically means, okay, now we know where we're started and we know what direction to go now, right? So if you will, if I say up 1/2, then I'm effectively saying I'm going to take off from this point, kind of aiming in that direction, right? And so, but of course it isn't going to work very well. If this is a curve, it's not going to work to go that way very far, right? We can't go very far. We got to go really small. And so we'll go just a little bit and we'll get to a new point and we'll reestablish ourselves at that new point. And so if we let our, let's say we let our change of x, and toward today, let's let that be kind of small, like 0.1 or even 0.01. We're going to use Excel and do this upright, but let's let that be really tiny. And so if that's the case, and we're sitting here at the 0.32, I'm going to blow this up a little bit. And we take off kind of in this direction. And so this right there will be our change of x. And of course, then this would be our change of y. Notice that isn't the same measurement. Those are totally different. So the question is, where do you land? What did we do back in that first section to figure out what this new point is? Now that we've cruised along, what did we do? And again, I want to give you a second, not so much to like re-look that up, but more just to reason about it. Where am I now? Where did I land? Now, of course, because we said our change of x is 0.1, then our x coordinate there would of course be 3.1, right? Because we let x grow by 0.1, so it went from 3 to 3.1. But 2 is not going to go to 2.1. What's the shortcut? What do I do to kind of figure out that? And of course, another way to label this would be dx and dy instead of change of x and change of y. That'd be the same thing.
Well, you have your change of x, which is that your slope? So if you did y equals m, which would be change of x, and then your x values plus b. I'm trying to think of that. I can't quite remember how we did it.
So dy over dx is of course the slope, which in our case is 1/2 right now, right? So in a sense, there's really just this, and again, I'm explaining this totally different than I explained it back at the time, just because I want you to think about this a little bit. But these two triangles would be proportionate. So dy to dx in our little triangle, this is like 0.1, and really that's the question here, is how much does y grow? How much did y get bigger? It started at 2, and now it's going to be what, 2.2, 2.05, I don't know, 2 point something. It's not 2.1, it's not going to be the same. And so the idea is there's just a proportion there, like those are going to be equal. So given that those two triangles are proportionate, then wouldn't you say that dy dx would equal, I don't know what, over 0.1? So then algebraically, doesn't that mean that, what I would like to know, the question mark is 0.1 times dy dx? So 0.1 times the slope. Well, that's what our formula was before. Basically, this answer right here is going to be 2, the previous y plus 0.1 times the slope. That was the formula that we used last time. We basically said this was your previous number, your sort of previous point, your previous y, So this was our, y of n, that's our sum term. This was our change of x. And this is our slope. And all of that together is going to give us y of n plus 1. In other words, our next y. Remember that little subscript. If you take 253, you're more comfortable with this than other people, but it's kind of like y of n is the n I'm at right now. In our case, it's actually y of 0, right? Because that was our first one. But whatever one you're at, this is how you get your next one, right? And so, boom, I just kind of plug all those numbers in. The slope is a half, 0.1 times a half, 0.1 times 0.5 is 0.05. And so in our case, that would give us 2.05. And so I just established myself at my new location. So then that's great, because we basically went as far as we think it's fair to go. And of course, it's already wrong because the curve, it's actually curving, right? But remember, 0.1 is a pretty small number, and we could certainly even go to 0.01 or even 0.001. But now what do we do? Like, how do we get to our next point? Let's do it again, right? Well, no. What's wrong with doing it again? Like, what do I need to know?
You need to do it from your new y.
Yeah, so I've got a new location. So just like I used 3.2 before, and that was great. Well, now I'm going to use 3.1, 2.05. Great, I got my new point. But what do I not have?
The slope at the new point.
Exactly. How did we get to proceed? We need a new slope. How did we get our new slope? Back then. And there's nothing here telling you the answer to that. Well, that came from the fact that we actually had an equation for that. In other words, we started out with some differential equation where we said y prime is equal to 3y. I better use a different letter or number. Like 4y minus 2x squared or something like that. Like we had a differential equation. Remember, we were saying, oh, let's try to solve that thing. And we were thinking to ourselves, oh, we're too dumb. We don't know how to solve that. We don't have any methods. Now you have methods. You're like, oh yeah, I got everything, man. I can take Laplace transform of both sides. I can subtract 4y over and use the mu technique on this one. I mean, I got all kinds of options. But at the time, it was kind of like, well, I don't know what to do with this. And so we said, well, the 0.32 works because that's your initial condition. So, and the slope is a half. And by the way, if I plugged 3 and 2 into this, does it make sense that y prime better be 1/2? Which it isn't, because I just made that up. Let me see if I could fix that really quick. That'd be 12 minus 8, which is 4, and 4 divided by 8. There. Now if I put 3, 2 in, the slope is actually a half. And so, and of course I could even make it multiply both sides by 8, or simplify that side and make it 2y minus x squared over 4. I mean, that kind of a thing. But that's what we did. That's how we got our new slope, is we plugged in, we basically found y prime of, well, 3.1 for x and 2.05 for y. So basically at the time then we said, if you have x, so this was kind of our sort of rule, our technique at the time, we basically say, if you want your next x, what do? You take your previous x and you just add whatever your change of x is, or sometimes that was called h. In other words, just add to it. It was 0.1, so 3 goes to 3.1. That's pretty easy. How do you get your next y? You take your previous y, but you add to it your change of x multiplied by your slope. And what was the slope evaluated at? It was evaluated at your previous value. Wasn't that it? And then that gives you your new location. And now you have, remember this, this right here is now our kind of our 3.1, and this is our 2.05. And then you just kind of start over and say, okay, cool. I just established myself at my new location. So then I'll plug these two values right here. I'll plug them back up here to get my brand new slope. And so now I just established myself. I'm at a new point. I have a new slope, and then I just do it again. And I do it again and again and again. And in that way, I'm just going to like creep along crazy. I'm creeping along the answer to this differential equation, even though I don't even know what it is. I mean, that's just really cool. It's just a really neat idea. And again, as I mentioned at the time, the cool thing is if you're an engineer, then you don't actually need to solve this differential equation. You can just create the graph for it. So let's do that. Let's remake that again, because we're gonna build on this idea today, except for we're gonna do this for a second order. What I'm showing you here is kind of just a brief reminder of the logic as to how the first one went. And again, for you future teachers, this is why I teach the way I do. When I brought this up, would you not agree with me that skill is mostly gone? Like at the time you had it, but now you don't have it anymore. It's gone. But if you took the time to reason it through a long time ago, then you would be able to get it back. It's still gone, but you would actually be able to get it back by logic. And that's the important thing. Otherwise, you might as well not take the class, because it's already gone and the class isn't even over, let alone 6 months from now, let alone a year from now. It's already gone. So let's go over to Excel. And remake a spreadsheet. And by the way, I'm changing your assignment. It's not the book assignment. It is the book assignment, but I'm gonna have you do it in Excel. And I'll probably, like I did last time, I'll post this Excel so you can steal it, which I maybe shouldn't do. Like maybe I should make you make this from scratch. So again, I like Excel because this is really blue collar. This isn't some kind of a program. I mean, I could do this, and I think I showed you at the time, we could make a little iterative program. If you're a programmer, you have better ways to do this, but this is a little slower, but it's just super transparent. That's why I kind of like it. So let's see, we have our X value, we have our Y value, and we have our, what am I going to call it? Slope. So I could say, and I'm going to say what it is, dy dx. I kind of like that better. Could have said m for slope. So we started at the point 3, 2, and I'll make those bold so they look different, and I'll blow this up. Is that any better? Do you care that it's blown up, or could you see it fine before? And so what do we do to get our slope? Well, according to the equation I just wrote, we say our slope is equal to, this is the language of Excel, it is equal to, let's see, it was 4y. So 4 times, and by the way, in Excel, just as a reminder, you have to say times. You can't just say y. So it's 4 times this cell, because right now y is 2. And then it was minus 2 times x, which is this, squared, and then go back and put parentheses around all of that because we're dividing by 8. And so that's not good, because that means I either typed something wrong, because remember it was supposed to be a half, and so I think I blew it. So I got to fix my equation now. I think I mixed x and y up is what I did. Yeah, 4 times x. So what I need to do, I apologize because I need to do this, I guess, really quick. I don't know if you heard me out loud, followed what I was saying out loud, but I went in there because I'm used to thinking of x first. And, what I did was I put 3 right there, and I put 2 right there. That's how I got 12. And then dividing by 8. Is that right? 12? I wanted the slope to be a half. So let's see. I got to fix this. So if this was actually 2 and this was actually 3, that'd be 8 minus 6, which is 2. Is that right? 8 minus, no, 9 squared, 18. That'd be 8 minus 18, which is negative 10 divided by negative 20. Did I fix it now? 3 cubed is 9 times 2 is 18.
Yep.
8 minus 18. Okay, it's fixed. So again, I was expecting to see a half and I didn't get it. And so, okay, divide that by negative 20 and I should see a half. So, okay, good, it's fixed. And so it's working now, right? Whew. And so what do I do? Okay, so there's kind of my first, my 0th term. You know, this is like n. I mean, I could add this. I don't really need to have this over here, but I think I'll just add it anyway. So you understand the language. So there's, you know, my nth, that's my 0th term. And now I'm going to move on to my first term. So let's do this kind of in a fun way. Like I could just type 3.1 here. Do you agree with that? Because I already chose 0.1, but let's do this in a way that's a little bit more fancy. Like I'm going to say dx here, and I'm going to say for now 0.1. So down here, instead of making this 3 plus 0.1, I'm going to make it 3 plus that cell. Except for what do I need to do? I can't just say 3. Anytime I want it to actually do the math, I have to say equals 3 plus that. If you put the equal sign in there when you click, it's like, oh, you want that cell. And so, yeah, that's what I want. And so notice, okay, great. That works. But of course, I'm going to want to copy this down. And if I copy it down, it's not going to work because, as you may remember, if you go up here and you hit F4, that will automatically throw the dollar signs in front of the C and the 2 so that when you copy it down, it will still read 3 plus C2. Now I realize, wait, I can't just make it 3 plus that. I have to make it the previous cell. So this one really needs to say not 3, but the previous cell. And so now if I copy this down, yeah, 3.3, 3.4, 3.5, okay, it's working. But what's cool about this is what if I went back and said, okay, let's do this more accurately. See how like automatic, I didn't have to do it again. So that's just kind of neat. And so what did we do to get our new y a second ago? What did we say the formula was? I don't have it up for you to see anymore, but what did we say it was? It wasn't x plus the previous x. It was the previous y. So this cell will be equal to the previous y plus the change of x times the previous slope. Wasn't that the formula? And so, okay, that's working, right? Because we got 2.05, so that's working. And then of course I want to copy this down. So which one of those do I want to move down? When I move down, D5 is going to move to D6, C2 is going to move to C3, E5 is going to move to E6. Which ones of those do I want to allow to do that, and which ones do I not want to allow to do that?
C2 needs to be locked.
Yeah.
Exactly. C2 needs to be locked because I want to stay looking at that, but the other ones I don't. Hit that little green check mark. Awesome. And then what about this formula? This formula says take 4 times D5 minus 2 times C5 squared divided by negative 20. Which ones of those do I want locked? Notice if I click on it, it shows which 2 we're looking at.
You should be good. Should be fine to go down.
Yeah, I don't want it to lock because don't I want the slope to be calculated? This slope is calculated by just looking at these 2 numbers and plugging them into the formula, right? So again, this is where Excel's really cool. Boom, there's my new slope. What am I not surprised to see there? I'm asking you to read my mind, but what am I not surprised to see?
That it's only slightly more than 1/2.
Exactly. It's really close to 1/2. Now it could have been a little lower, like 0.48, Could have been a little higher, but I didn't move very far, right? We only went 0.1. So of course that hasn't changed very much. And of course, if I go over here and make it 0.01, you know, what's going to happen to that slope? Now look how little it changed, right? So it's like a tiny little step. Well, of course, the slope hasn't changed very much. It's kind of cool, right? And so I guess I'm done, aren't I? Like I don't have to make anything else. I've made all the formulas that I need. And so I can now, and as kind of, and I think I showed you this before, but it's kind of, there's some other cool tricks you can do. One of them is if I copy 1 down, it kind of doesn't know what to do with it. But if I grab 0 and 1, it kind of like reads your mind and says, oh, you went from 0 to 1. You must be going from 1 to 2. So I could have done that over here with the 3s. Does that make sense? Except for I didn't want to do it there because then it wouldn't have updated when I changed this number. And so, you know, I don't really need these ends over here, but let's just go down there. So it's like, I'm going to find 16 points and then graph them. In this case, I wrote a cool formula, so that'll take care of itself. And I can just grab both of these at the same time and then boom. So notice I just made this up randomly, but notice the y is getting bigger, 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 bigger. And the slope is getting bigger, 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 and x is getting bigger, bigger, bigger. And so what does the answer to this differential equation look like? It's really this graph right here. It's just a graph of all the x's and y's. Does that make sense? So I can go up here and I can say insert and go to this one right here, a scatter plot. No, this one, a scatter plot. And there's a picture of the solution to this graph. And I have some choices. I can connect them and so forth. And of course I can go further, you know, get more ordered pairs. And, you know, this doesn't that look like an E? It looks like an exponential function. And so maybe maybe it'll be really fun and it'll get up there a while and then, you know, it'll dive down and so forth. But let's just do this. Let's take it just a little further. To where it makes it to 5. And so here's a cool trick. If I grab this, notice it says, hey, look at the data that you have over here. Well, I think I can actually grab these and just drag them down and say, I want that to actually be this now. And so as I said before, and I really want you to leave this class understanding this, if the engineer's goal is not to find the equation y of t. Do you understand that? Their goal is to find that and then use that to answer a question. And so we started out at the point 3.2, and really the main point might be like, okay, that's what's happening right now. At time 3, there's 2 kilograms of salt in the tank. But what I'd like to know is how many kilograms of salt are in the tank at time 5. And does it make sense I just answered that question without having to actually find the equation? Now, of course, the curiosity would be, if I, you know, bumped the time change down, would that make a big difference? You know, is this 4.07? What's it going to change to? Is it going to change to like 5.2, like a really big change, or is it going to be like 4.08? Is it really not going to be that big of a deal? And so, you know, I don't know about you, but looking at that graph right there, that looks pretty good, doesn't it? It doesn't look like 0.1 is kind of okay for a step. I mean, it kind of looks like that'll probably be reasonable. But obviously, if I really wanted to do this right, I would just make more steps. And of course, to do what I just said, notice that took me 20 steps to do this. Well, if I take this and make it 0.01, now it's going to be 200 steps to do the same thing. Does that make sense? And then these dots are going to be so close that you're not even going to be able to tell they're different dots. And that'll give me a slightly different answer. And so, you know, just for the fun of it, even though I don't know if it's going to be fun, let's do that. So let's take it down to, so let's first of all change this to 0.01. And now we're a long ways from 5. Actually, yeah. We're a long ways from 5, and so now I got to get down to 5, and so I just got to drag this down until I make it to 5. Let's see, would we say that would be 200 steps? So I'm gonna have to be down in the 200s somewhere. So that's cool. And just because I want to get rid of it, I'm going to right click and say clear contents. And so there I know where to stop now, so I can drag everything else down. And I'm not great at Excel. I think there's kind of some cool tricks to this, like dragging stuff. This is where the computer programmers would be gagging at this. Like, and notice there's our new answer, 4.11. So it went from 4.07. It's a little more accurate now. And of course, to change the way the graph looks, notice the graph stops short. Let's see, is there a way to grab both of these at the same time? Apparently not. Whoa, chill pill. So I want the whole graph now, which is going to have a lot more ordered pairs. This graph kind of, so it's like the same graph we had before, but as I said, notice it's kind of touching now. And so doesn't it feel like, wow, that's accurate enough? Like, let's not go to 2000 points. This feels pretty accurate. It didn't change that much. It was only 0.04 off, 4.07 to 4.11. So it kind of feels like, yeah, that was a waste of time, unless I had some really weird precision reason. And so this is what you're just to make sure you understand your book question. This is basically what it's going to ask. It's going to say you start at, some 0.32. Y of 3 is 2, or y of 0 is 8. Notice it's kind of cool here. Remember how much trouble that caused us when we were solving these, that this initial condition didn't start at 0. Remember how that was a pain? Doesn't matter in this world, like start at whatever point you want, who cares? But remember, Laplace transform needs y of 0, and we don't have y of 0, we have y of 3. So it's like we'd have to slide the whole thing left. So we had y of 0 and then slide it all back again. And, again, the engineer, the non-mathematician would say, why are you doing any of that stuff? We can solve all this stuff numerically. So quick reminder, but now what we want to do is add to this the fact that it is a second order differential equation. Could we do the same thing with a second order differential equation? So let's go back and do that. So the question is, let's see. I'm inclined to pick like a question off your last test or something that we know the answer to. I'm pulling up the key to that. Find one that's kind of interesting. Yeah, question 3 has got a bunch of sines and cosines in it, so that looks like that could be an interesting answer. So this is going to be question 3. So that's kind of a quick review. But now what we're really seeing in this chapter is what about this? So if I say y double prime minus 6y prime plus 34, plus 34y equals 50 e to the 3t. And you were given the initial conditions y of 0 equals 5 and y prime of 0 equals 10. And when you were all done, because I was nice to you, when you were all done, you actually found the solution to be y equals 2e to the 3t plus 3e to the 3t times, actually, let's just write it this way. Since both of these have it, then there was like a cosine of 5t, and then there was a sine of 5t. This was your solution. And that was a lot of trouble, right? We took the Laplace transform and we had to make up a proper guess and separate out all those S's, and then do a 3x4 matrix to find the A's, B's, and C's. And then we had to rewrite that as a Laplace transform. And finally, and that's really cool. Absolutely. I mean, I'm not downing that at all. That's just really, really cool. But the question is, could we get this answer? We'll get this graph. Could we produce this graph in the same way we just produced that graph in Excel? Could we do this in the same way somehow. So I ask you this question. What does y double prime mean? I haven't done my job if you don't know the answer to this question. And I'm talking to people that have taken
Is it concavity?
calculus sequence. Go ahead.
Is it the concavity?
Even simpler, like it tells us something about the concavity of a graph, but think of it as y prime except prime. Think of it like that. Like what is that? And you're right, David, it is concavity. What does the derivative mean?
Slope or the rate of change? Is it the slope of the
Yeah. That's exactly right. And that's kind of what we did back up here. Like, didn't that slope up here mean the rate of change? It basically told us how is y changing? It's y is 2 right now. And how is it changing? It's changing by a half. And so by setting up that proportion, we were basically able to say 0.1 times a half, then will tell you how much change there actually was. So it was a rate of change. That's what slope means, is rate of change. But then this would be the rate of change of the rate of change, or I guess you could say the rate of change of the slope. Because slope and rate of change are the same thing. So I'm basically thinking of this as the slope. I'm rewording that as the slope, and then this is the change. So it's like the change of the slope. Isn't that what a second derivative is the change of slope? So just like a second ago, we found the rate of change of the y value. Couldn't we even use this formula, this y double prime, to find the change of the slope? In other words, we know what the slope, we had a formula back here in sort of this first chapter that told us what the slope was, but now we actually have a way of finding the rate of change of the slope. So even how the slope is going to change. Let's think about that. So then, oops, that's not what I wanted. So first off, we have what we had before, which is if you want to find your next y value, what do? You take your previous y value and you add to that your change of x. And just in case, I don't remember what's in the book, but a lot of times that's also called h, but change of x or dx is probably a better way to say it, times y prime. That's what we just did a second ago, right? Of the previous location. Well, in the same way, how do you find your derivative? How do you find your derivative, your next derivative? How do you find your next slope? Well, exactly the same. You take your previous slope and add it to your change of x times your previous change of slope. Does that make sense? It's exactly the same formula. So just stop and make sure you take that in a little bit. How do I find my next n plus 1? How do I find my next slope? I take my previous slope and I add to that the change of x, 0.1, times my change of slope. How's my slope changing? Multiply it by this, add it to the previous slope, and then you'll have your new slope. So let's see, what does that look like? Let's kind of do this manually a little bit, and then we'll jump to Excel. So, okay. So I've got my X term here, which started out, what did it start out at? I've got my Y term here. What did it start out at? I got my Y slope here. What did that start out at? Well, I started at the point 0, 5, right? That was my initial condition. My initial location was 0, 5. And I was even given my initial slope, which was 10, right? And so how do you get y double prime? Well, notice if you take that original equation up there, it has y double prime in it, but maybe it would be more informative if you solved it for y double prime by, adding 6y prime to the other side, subtracting 34y to the other side, and then leaving your 50e to the 3t on the other side. Isn't that what you do? So to start with then, don't I just plug all that junk in? Like, this isn't hard. So y prime is 10, so I'm going to throw that 10 in right there. And y is 5, I'm going to throw that 5 in right there. And then there's a t, and that t was 0. So maybe I'll switch this instead of x and y. Maybe I'll just write both. So I got two choices. I could just switch that t to an x in the equation above. I kind of want to leave that as xy because I want to think of it as an xy point. Does that make sense? So I don't really want to switch the x to a t because then I'm thinking you're going to go, what? I'm graphing, t, y. What are you talking about? I mean, that's what we were doing the whole time, but basically that's our x term, our t term. Those are the same thing. And so, yeah, look, I have everything I need. So if I plug that all in, let's see what happens. 6 times 10 is 60 minus 34. 34 times 5. E to the 0 is 1, so that'll be plus 50. 34 times 5 plus 50. When I do that, I get negative 60. What does that mean? What does that mean? We started with a slope of 10. That's what our slope is right now. And notice that's a really steep slope. This is probably going to be a really weird graph because that's a really steep slope to start with. 10 is almost vertical. But what are you being told about the rate of change right here? How's the slope going to change? What's it going to go to next? If it was 10, it isn't saying it's going to be negative 60, but what's going to happen to the slope? Is it getting bigger or is it getting smaller?
Smaller.
It's getting smaller. That negative means decrease. So it's getting smaller and it's getting big time smaller. Does that make sense? So I don't know what it's going to be, but it's not going to be 9. You see what I'm saying? It's not going to go from 10 to 9. It sort of feels like, wow, that is massive. It is really going to get small after this. And so, okay, great. I just established myself. Now, what do I do? How do I move on to get my my next ordered pair? Well, remember, it all kind of hangs on what you decide your change is going to be. So we'll make that change 0.1. So that means my x in this case will grow to 0.1. How do I get y though? Well, that's what we just reviewed.
Just use the slope, right?
Yeah. What does that formula up there say? It says take your previous y, 5, add to it h, which is 0.1 times your previous slope. Well, don't we have our previous slope? It was 10. All right. So it's like we don't have an equation for it, but we don't need an equation for it. So I'm going to go up here and plug in these values. I'm going to say, okay, well, this is 5. That's my previous y. My h is 0.1. My previous slope is 10. 0.1 times 10 is 1. 5 plus 1 is 6. And so my y just jumped to 6. Agree with that? How do I get my next slope? Well, that's what this equation's for. I take my previous slope, which was 10, I add that to the change of x times my previous change of slope, which was negative 60. So 0.1 times negative 60 is negative 6. 10 plus negative 6 is 4. So, hey, look at that. Sure enough, it got smaller. Again, notice it didn't go to like negative 50. It just got small really fast. And so it got smaller. So it went to 4. Awesome. Notice I have my next point. Like this was my 0th. Now I have my sort of my first point. And so all I need to do then, and now we're in repeat mode. Now I take these numbers, ding, ding, ding. And just like we did before, I put those back into this expression to see what my next slope will be, right? So 6 times y prime is 4, so that'd be 24, minus 34 times y, which is 6. And I'm only doing this so that the second we go to Excel, we can make sure it's working, right? Because when I try to write a program for this, I'm going to probably screw it up like I did a minute ago. So minus 34 times 6 plus 50 times e, and e is no longer raised to the 0 power. It's now e to the 3 times 0.1. So 50 times e raised 3 times 0.1 is 0.3. So it'd be raised to the 0.3 power. So I might have tucked all that in wrong, but I got like negative 112.5. Just quickly double check that just to make sure. 6 times 4 minus 34 times 6 plus 50 times e to the 0.3. Yeah, that's good. So notice, wow, that's even changing more. And so I'm expecting the slope, which went from 10 to 4, to go down even lower now. So maybe it's going to move into the negatives. Maybe my next step will move into the negatives. And I won't write any of this down, but let's quickly calculate. Maybe you do this with me because I'm going to do it faster, which means I'm probably going to screw it up. So let's see, I take my previous y of 6, and I add to that 0.1 times my slope, which is 4. So I got 6.4 for this, I think. And then to get my next y prime, I take my previous y prime, which was 4, and I add to that the change of x times my previous y double prime, which was negative 112.507. And I got negative 7, approximately negative 7.25. Again, that sort of makes, at least it makes some sense, because this would indicate 10's going down. This would indicate 4 is going down even faster. And so it went down. So that's kind of feels right. So again, I might have punched a button wrong there, but I don't think so. So either take a mental or physical snapshot of that with your phone, because I'm going to switch over to Excel now. And we're going to see if we can kind of produce the same numbers, except for then with Excel, we're going to say, hey, good, we don't have to do this anymore. Let's just, speed down to 50 answers and get a graph, right? I mean, we're going to get a visual of the answer to this thing without ever even being able to solve it, right? So let's see, I think I'll leave that in there rather than erase it. And I'll just go to a new page. So again, I want to let dx, maybe this will help you. And x, y, this time I'm going to say y prime and y double prime. And we started with our 0th number. We started at the 0.05 with a slope of 10, this initial slope of 10. And now it was like programming from there, right? So center those dudes, darken those so I can focus a little bit better. So then we said, okay, how do you get y double prime? You take, we said 6 times the, in our case, 6 times, and by the way, this is where an iterative program would be better, because notice I'm typing one particular equation in here. And then if I want to use this for something else, I would have to type a different equation. But notice it's the first time I'm typing an equation. So it was 6, in our case, 6 times y prime. Well, y prime was being that number right there. And then it was minus 34 times the y number, which is, bam, that number right there. And then it was plus 50e to the 3t plus, anybody remember how to do e in Excel? It isn't e, unfortunately.
I think if you type like capital E, it should be exponent. Like it should come up with a option for you.
It's EXP. Notice it says returns E raised to the power of the given number. So there isn't an E. This isn't a math program, Excel. So they have exponential in there because exponential growth is the thing, but you don't get to type E. You got to say exponential and then put in parentheses what you're exponentialing. So I actually don't think I even need this parenthesis. The important parenthesis is this one where I say, what is E raised to? Well, it was 3t, right? So it's raised to the 3 times t, which is, you know, this number right here. That's our x or our t, our x value. And so that's how we got our y double prime. And so, okay, good. That's right. That's what we're supposed to get, right? Negative 60. So that seems to be working. That's really cool. So this cell here is going to equal this cell plus whatever our step was. That's how we got our next number. And we said last time that if we put dollar signs in front of that, which you can cheat and hit F4 to do, you get that next number. And I think I'm going to do the same thing here. Matter of fact, I could just copy that over, couldn't I? No, I can't. That's not right. So I got to say this cell equals this cell plus 1. Does that work? Yeah, that cell equals the previous cell plus 1. So that works. So that's working. Okay, that's great. So what did we say again? How do we get our next y value? That's right. We take our previous y value and we add it to the change of x times our previous slope. Wasn't that our formula? And then we said, again, that D2 needs to be dollar signed so that I can copy this thing down. And so is that working? Yeah, 6, that was our answer, right? Went to 6, that's rad. And then let's see, we do the same thing for this one. We say, how do we get our next slope? Well, it's equal to our previous slope plus our change times our change of slope. And we dollar sign that dude. Bam. And so that's working. We got 4. And then fortunately this one, remember, was, and you can click up here to see it, it was looking at only these cells over here. In other words, it was found by looking at all of these. And so that means I'm done. I can just take this and copy it down. And so, okay, good. I didn't screw that up either. It's a miracle. And so every one of these now has a formula in it that is written correctly, and because I did that, which means I can actually grab all of these simultaneous now and just drag them down and I get the next line. So is this line working? Yeah, I got 0.2 here. I got 6.4 there. And my next number was negative 7.25. So I didn't type any of my numbers wrong. And so this thing is working. And notice the slope is continuing to blow up negatively, if you will. It's almost like hard to even comprehend what that's saying. So again, that's just kind of drag it down slowly and watch what's happening. It's like, yeah, this change of slope is just getting more and more crazy. Let's drag it down a little ways. Notice what's happening to your ordered pairs. Notice the X's are growing predictably slow, but look what's happening to your Y's, 5 to 6 to 6.4. Oh, that's interesting. It was getting bigger, and then all of a sudden it started getting smaller. So right here, it actually started getting smaller, and then it, well, actually, look at that. It went down to negative 25, and then it started getting small less quickly. And then it actually started getting big positively. Isn't that interesting? So this is kind of a fun, that's why I picked this graph. But then even look at the slopes over here. Did you notice they were negative and then it actually went back to positive? It's like, nope, now they're growing. They were getting smaller. Now the slopes are getting bigger, 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 bigger. And then they started getting, they got their biggest right here at 6,000, but then it dropped to 4,000 and then 700, and now it's negative 7,000. Like it's this crazy graph. Isn't it weird? I mean, it's just kind of fun. So let's take this out to 2. And so our goal here is to say, hey, we started at the 0.05. Again, times 0, I have 5 kilograms of salt. And what the way your book assignment will word this, just so you can kind of see the language, is it'll say this relationship exists on the interval from 0 to 2. So time 0 to 2. And so they're basically saying like, what's happening there? And then the answer to that question is 1,124. So we started out with 5 kilograms of salt. And although it went, up and then down and then up and then down, it ended up with 1124, so to speak. And notice salt doesn't make sense because you can't have negative. But of course, the interesting question, of course, is like, man, what does that look like? So again, I'm going to insert a scatter plot. And notice you have some options here. You can actually look at them ahead of time. You can connect them. You can get rid of the dots. You can have a smooth curve connecting them. It tries to connect them with a smooth curve here. Doesn't have any at all. Here it connects them with straight lines. And so it's kind of jumbly looking. Here's straight lines with no points at all. Probably for us, that curved one would be the best, right? And of course, I find myself looking at this thinking, that's pretty interesting. But it's like, man, what's going to happen next? This is kind of cool. I want to sort of see a little further. So I'm going to take this down to 3 just for the fun of it and see what's going on down there, which should be another 10 spaces. And so let's click on this and drag it down to 3. So notice it went up so high that a second ago, that big dip that you saw was actually right here, but now that's such a tiny amount that it got kind of overcome by this. And so that's pretty interesting. Now, of course, the interesting thing is, one interesting aspect of this is notice you can't really recognize what you're looking at there. If I kind of go back and I don't see that, but notice there's a little bit of an up and down right here that you can't see very well because again, this made it up to 1400, which kind of screwed up the scale. But what did we say? In our case, we actually knew the answer to this question, right? I gave that to you. So let's go to Desmos and see, what is the graph of this thing actually, what is it? Graph supposed to be. We never kind of did that in the problem, but I wrote down for you a second ago that the answer to this was really 2e to the 3t, 2e raised to the 3t, and then it was plus 3 times e to the 3t, which means I could have factored e to the 3t out of everything, but I guess I won't go back and do that in the interest of time. And then it was times cosine of 5t. plus minus the sine of 5t. So the question is that what we were seeing a second ago? Now this isn't super satisfying because notice this graph only goes up to 10, whereas a second ago, you know, our graph went up to 1400, right? So I'd have to set the window the same, if you will. So let's see, what is the window? 0 to 2.5, 0 to 1600. So fortunately I can do that in Desmos over here with this wrench. 0 to 2.5 and 0 to, what did I say, 1600, something like that. So yeah, that is what we're seeing. And so as I mentioned, we're not able to look at that and go, oh, I recognize that equation. But can you see how the engineer could get not the equation, but the answer the equation produced by doing this? I mean, isn't that kind of cool? Now, what's really cool about this? So in a sense, it's kind of like cheating, like you're cheating to get answers, so to speak. And again, of course, this isn't available to all of the people in history, right? Except for us in the last 40 years. Nobody gets to do this, right? Because we just got a bunch of free basic math. It was all add, subtract, multiply, divide, but it was like a bunch of basic math, and we get it all for free. So although what I showed you today was theoretically kind of cool, it wasn't very practical cool without at least a basic handheld calculator. So in one sense, as I kind of like to say, you don't actually need anything I'm teaching you here if your goal in taking this class is to be able to do something practical with it and model something. As I mentioned before, it's like, you know, solving these equations is pretty hard and pretty time consuming. And so in a sense, maybe you get some cool points, but there's a lot of room to make errors in all this. And so, you know, man, this is kind of a pretty compelling idea, I think. Now, I want you to consider this example. and actually what I would like you to do is, since you're sitting at a computer and, you know, maybe you can do this, but pull Excel up, like try to do this for yourself. And I'll do it kind of for you after that. But see if you can write your own program. Don't just like steal over the top of mine. But before you get super into this, I want you to consider this particular example and why I'm giving it to you. And I'm actually grabbing, a lot of times I make up stuff randomly, but this particular one I'm not making up because I did make it up before and it's cool. That's why it creates kind of a neat graph. That last graph, if you will, kind of went out of control. It was a cool graph because it had some hoop-de-doos in it. It wasn't like that first one that just went, you know, it was kind of dull. So this particular graph turns out to be really cool. But before you kind of try to solve this, I want you to stare at this for just a second in the context of what we've been talking about. So if I gave you that on the last test and said solve, there's a big problem with that. Do you see it?
That t squared.
That's precisely right. What was always in front of the y double primes and y primes and y's?
Constant coefficients.
Always constants. And so you can't do this. There isn't a way to do this problem, at least with what we know in this first course. But again, this is the heartbeat of true mathematics is, and I did mention this once before, but it's like, what if that, you know, what if we start messing around even more? Like, what if you grow these in complexity? What if those aren't just constants? What if they're t's? What if they're even y's? What if that, you know, y double prime in front of it has like a y, you know, not even the independent variable, but the dependent variable, you know, what then? I mean, how crazy can we go with these and actually find an answer? But you're not going to be able to take the Laplace transform with that t squared there
could you use that? Is there not a dodge, like the t to the n times a function or something?
That's exactly right. And so that's what mathematicians would do, is stare at this and see, you know, is there some kind of a dodge? Is there, and, you know, you use the word dodge because that's the word I used on the Laplace transform sheet. Wasn't there a way to take a Laplace transform? Wasn't there like a shortcut? This is what, I'll take a quick look at that. Wasn't this cool dodge on my sheet right here? Wasn't this one addressing how to handle that? Didn't this say, hey, if your function has some t's in front of it, t squared, then maybe you could pull this off? And so good for you, David, to think of that. Like maybe we could actually pull this one off, even though it sort of feels painful. We might be able to pull that off. And notice we have a dodge for if there's an e. So I could put an e to the at in front of something and maybe we could still pull it off. But there doesn't seem to be a dodge for sine. In other words, what if I went back here and replaced that t squared with like sine of t or something? Does it make sense? You know, now it's like I'm going to need a new dodge, or, you know, maybe there's no way to do. I mean, I don't know what's going on, but again, what's kind of cool about the technique I'm showing you is we don't care. Like, does that hurt anything that there's that there? No, doesn't matter. It's easy. Now I do have to give you some initial conditions. So, because we have to have a starting point, and I made these up at random. So at least originally, what I can't remember is if I played with these to get it to be something cool. So there's your initial point, 0, 1, and there's your initial slope, 2. And of course, the important thing here is to, you know, kind of resolve this. So I don't like minus signs in the front, so I'm going to add 4y over to the other side first, and then subtract t squared y prime, and then leave all the other junk there. So the question is, could you write? Let me see. Let me read the way the book words this precisely, because this is what the book questions are going to look like. 5.3. Just so you understand the language, because you'll get confused when it's not confusing. Yeah, so it'll add to these two statements right here. It'll say this, and nothing else. It says nothing else, but it says on 0, 4. What does that mean on 0, 4? That's kind of our third condition, so to speak.
Means you go until 4 and then you stop with increasing your x's.
Yeah, the key is these are the x's, or in our case, the t's. So we started at 0. Yeah, that's where we started. T is 0, but we're going to go to t is 4. And we basically just want to know the answer. What's y? So what I want you to do on your assignment is modify a little bit what's in the book. I want you to graph all of the points from t is 0 to t is 4, make a graph of it and take a phone picture or whatever, you know, to get that to me. And, you know, and then of course, answer the question. And then the second thing I want to do here, just because it's kind of cool, is let's make h, or the change of x, 0.01. In other words, really accurate. Now that's kind of painful because notice that's 400 values we're going to have because we went from 0 to 4. But if we go in steps of 1/100, that's going to take 400 steps. And so, I mean, if we're going to do this in Excel, let's take advantage of Excel's properties. Instead of just having 40 steps, let's do 400 steps. Like this is your assignment. I want you to use this value. Wait a minute, maybe we'll even make it worse. Actually, let's not talk about your assignment yet. Let's just do it. I'll explain your assignment later. So the question is, can you get Excel working? Or if you don't have Excel, at least kind of write out the first couple steps to this and kind of get it rolling. I think it's a good idea to punch a few calculator buttons, kind of like I did. At least get the first 2 rows kind of filled out, kind of just punching calculator buttons before you go to Excel, because it's kind of hard to write the program, you know, accurately, since you're not getting to click. You're clicking cells and all that. As soon as we're done with this question, we're done for the day. So I'm going to do this with you. Because t is 0, you can almost get y double prime in your head on this one. I don't know if you noticed that. So, you know, if I get any of those wrong, obviously you're going to make everything else after it wrong. And so at a glance, I see y getting a little bigger. I see y prime getting a little bigger. I see y double prime getting a little bigger. Everything looks okay, but you know, maybe I punched a button wrong. Maybe I transposed a couple numbers and when I wrote it off my calculator, but can you do that? Like that's the main thing. I almost hope, I really don't like memorization, but I just hope that you can kind of say, well, this is my, maybe I'll be a little more accurate here and go in and put an N. This is my 0, 1, 2. That one right there is my Y2. How do I get my Y2? I take my Y1 and add to it my slope times my Y1 prime. That's how I got that number. How did I get this number? How did I get my y2 prime? I took my y1 prime and added to it 0.01 times my y1 double prime. That's what I think I typed in. And then of course I get this last one by just plugging all of these values in this line right here. Not really the two, but those blue values into the equation that's right here. In that way, again, miraculously, I'm literally walking along the answer to this, the graph of this problem. Any comments, thoughts? You cool with that? All we're really using is this. I think I have this on the note sheet for this class. It's the last thing on the note sheet since we're almost done. I think that's what I put for Newton's method. Let's go take a look. Note sheet, where is that? Do I still have it in here? Was it under Laplace table? I think it was under this rules, yeah. So this rules, back when we were doing this, Euler's method for solving higher order equations numerically. Notice I wrote it slightly different for you future mathematicians. I probably would have wrote it this way if I had thought about it, but can you still read that even though I wrote it differently? Can you read the language of subscripts? How do you get a particular value? Take, well, and -1, the previous value. So instead of saying this is how you get the next value, I say this is how you get a particular value, take the previous one. It's just like the same language. And then I used h instead of change of x or dx. Okay, let's go to hopefully you're already trying this and ahead of me, but let's go over to so. So this is kind of cool because I want to save a little time this time. So what I'm going to do this time is I'm going to go to right here. Have you ever done this? You go to this spot right here, you right click and say copy. And then I go down here to the plus sign, add a sheet, go back there again, right click, say paste. Boom, I have the whole thing over again. So, you know, it doesn't look like anything has changed except for the size of the sheet.
You're not
But now I'm going to
sharing.
pirate this. So I'm going to change this to 0.01 this time. My initial,
You're not sharing your screen, Doug.
not sharing my screen, dang it. I did all that. You didn't even get to see it. Now I'm going to do it again. So how to copy, go up here to this little triangle, which grabs everything, right click, say copy, go down here to this little plus sign, add a sheet, go back up there again, click on that, right click, say paste, boom, now I got everything. And now I can steal this for kind of my second problem. You might want to do that because you have two problems in your assignment tonight. So that, fortunately, I wrote this in a way that, you know, all that just updated automatically. So my first two, you know, columns here are already good. I don't have to do anything to those. But I didn't start at y of 0 is 5. I started at y of 0 is 1. Notice that whole second column automatically updates. I started at y prime of 0 equals 2. And then of course I have a totally different formula here, right? I didn't do that same thing. So this part I've got to rewrite completely. So what did we do to get this? We said equals 4 times y, 4 times that, minus t squared times y prime, minus this squared times y prime plus e to the t, which again, we have to say exp to the t power. T is this number here, boom, again. And that's multiplied by the cosine of 2 times t, which is this number here. So, of course, I'm looking at my notes to see, did I get 5? Oh yeah, I got 5. Good, so I typed that in right. I'm gonna go back here too and put x/t, since that's the label. And so is that it? Am I done? Can I just copy this down? Is that it? I think I'm done. To begin with, I want to go slow and just going to make sure this is working. That was wrong. Let's see, what did I do wrong there? Yeah, I didn't have a line. I didn't have a. That was a constant, so. Is this formula already correct? Can I click on it? Yeah, that formula is already correct. So I think these formulas are good. I don't think I need to change those. I think I just need to copy this one down. So is that my second line? 0.1, 1.02, 2.05, 5.08. Yeah, that's right. And so it's this that I need to copy down. I did one more line, and so I'm going to copy this down. So is that my next line? 0.02, 1.0405, 2.101. Yeah, 5.18. Good, it's working. So now I can just grab this and copy it down. Now in my case, I'm going from 0 to 4. And so that's like 400 lines down, and I'm at 6. So I need to be down at like 406 or somewhere in there. So I'm looking at those numbers on the left. So that's not terrible. This takes a little bit of time, but I don't want to have to do this again. So somewhere down in here, that'll get me farther than I need to go. And so I just needed to make it to 4. And so just so that I simplify my brain a little bit. So it's like, that's where I needed to get. And so notice the answer is 74. Like in the book question, they just wanted that because, you know, they weren't thinking Excel. Their step was huge. They can't have you go from 0 to 4 because even at a step of 0.1, that's still 40 of these. If you're going to do this by hand, that doesn't work. So they're going to say go from 0 to 1 in the book, not 0 to 4. But in Excel, we can take a tiny step and go a step as far as we want. So, you know, in the end, the engineer wants to know 74.65 and then they're done with this, right? We didn't want to graph, but of course we're just curious because we're curious humans. Because this graph literally represents the solution to this. I want to go grab all those X's and Y's, or in this case, T's and Y's, and insert a graph. Since I grabbed all those, I'm just going to start over and insert a brand new graph. I kind of like that curvy one a little bit. So I'm just going to go grab this one and say Control X, you are gone. And so that's cool. So we don't know where it's going to go from there, and we don't recognize that graph. I don't recognize it. It's kind of starts with an upward curve, and then it goes with a downward curve. Maybe it's a sine wave. I don't really know exactly what that looks like, but it's like we're literally looking at the solution to this differential equation. But a graph is better than an equation, right? Because if I want to know something now, like I can go over here to 2 and figure out what 2 is. I'm going to have to go over here and look at it, but I can figure out any answer I want from the graph. I don't have to do any algebra. So it's actually way faster. And of course, I can just copy it down further to get more answers. So this is kind of cool. This is kind of powerful.
And you could just use curve fitting and make an equation with that too.
Beautiful. And this is a place, I'll show you this really quick. But you notice the equations that we have access to with your graphing calculator and with Excel are actually really limited. So if I remember how to do this, if I click on it, right click and say add a trend line, it's kind of a weird word because it's not really a line. You have here the options. You only have the options here that you study in an algebra class. And so notice it's not a line, it's not a logarithm. It doesn't like some equations have limitations on their domain and range. Like they can't, notice this is saying you can't have a 0 value for something. And so it's like it kind of rejected that as an idea. Is it a polynomial? Order 1, order 2. It's like, you know, there's a decent one. Notice I can't see the curve anymore because it's kind of seems to be on it. So I found a cubed. And again, this is really fascinating because I think you can predict that the actual mathematical answer to this is not a cubed equation. Do you agree with that? Yet this is a decent model. Isn't that kind of cool? It's an approximation model of it. That's kind of neat. I'm gonna just check and see if any of the other ones work. Why did that go away? It didn't seem to like a power equation. What was wrong with the power equation? It's probably gonna do the same thing again, but I'm not sure what was going on there. But it liked a polynomial of order 3, so let's display that equation on the chart. That's kind of fun. But remember, because you did this on a previous assignment, the cool thing about Desmos is you can make your own equation up. But the problem is you've seen what these equations look like. They've got, you know, polynomials and e's and cosines and sines, and it's like, man, there's who knows what this answer could be. But that's kind of interesting that that curve is so accurate. I can't, unfortunately, because there's such a fat dot on here, I can't see, you know, the cubed apparently is staying inside it, but it's such a fat line, I can't really tell how good of a fit that was. There was one other thing though, I don't think you may not have noticed this, but there was something else I could turn on, display the R² value. What does that tell you, mathematicians?
How good of a fit it is, roughly?
Yeah, and what does that tell you? Is that a good fit?
It's a very good fit.
It's a very good fit. Couldn't be said any better than that. 0.999 means it's 99.99% accurate. So although that isn't perfect, wow, that's a pretty good model. Now, will it continue to be good if we went out to 10 seconds instead of 4? Maybe it'll blow up because, you know, we've seen these go crazy. But if you only care, you know, about this, if you only care from 0 to 4, that actually would be a really effective model for this. But again, is it really even necessary? No, because don't I have every single order pair over here? If I wanted to use it for something, don't I know? It's like, yep, I know what it is at 1 second. It's 7.259. Do I have to go plug 1 into this cubed equation to get that number? It's not even going to be perfect, and I already have the better answer right here. Does that make sense? But you know, for what it's worth, it's kind of cool to be able to find an equation. And you can see that, you know, because I did that last one pretty fast, you can see that if this was a thing for you, you know, you could actually do this really quickly and accomplish everything you would need kind of in the real world. So again, this is one of those times, and it's like, are you a true mathematician or are you a person that likes the practical aspects of it? Because if you're a true mathematician, it bothers you that we didn't find the exact equation. All right. So make note of this, and then we are done. Sharing a screen so that I can write this down. So your assignment, if I remember right, was questions 10 and 12. Yes. But I want you to just use a separate set of directions. So I just want to kind of formally write those down. My iPad does not want to share. I got there. So assignment directions, assignment. Two changes. Uno, H is 0.001. Because they are only asking you to go from t is 1 to t is 2, or t is 0 to t is 1, this is going to be 1,000 steps. You're going to make 1,000 steps to get just from 1 second or 1 minute or whatever. So leave the directions alone, but change h. They're going to say 0.1 or something like that, or maybe 0.25 or something. We're going to take a really short step. Secondly, I want you to graph. Give me the graph. And they're asking, they will be asking for the answer. In other words, if so, kind of as an example, if they said, you know, do this on the interval from 1 to 2, like that, they do want you to answer the question, you know, what's y of 2? Does that make sense? Like, give that last answer. You see what I'm saying? Like a second ago it was 74, you know, write that down, or, you know, note that, because that's the reason you would do this in the real world, is to say, I want this to exist from, you know, 1 second to 2 seconds. And then, you know, the whole point is like, what happened to 2 seconds then? You know, in the real world, you wouldn't need a graph. I just want you to look at it. And of course, if you find this kind of fun, I'll just say it in slang, just go find a cool one. Like, that's what I just did. I just made this up. I made that up right there. And because it really doesn't matter how hard you make these up, right? It doesn't matter what you put there. It's like, you can put anything you want there. Play around with it a little bit. The only thing I would say is I did this and I noticed that you get wildly different results depending on where you start. And I'd like to show you that really quick if I could. So this particular problem, you know, I just kind of made this up, but you know, what would happen if and this is what's kind of neat about Excel, what would happen if I said you didn't start at 0, 1, but you started at 0, 3? You know, does that change anything? And what if the original slope wasn't 2, but it was 1? Does that change anything? Or what if it was -1? Notice it's kind of like it seems to be behaving about the same, like it didn't change that much, if you will. So what if my, you know, initial y was like 32? Still didn't really change that much. What if my initial slope was -12? So I'm getting totally different, you know, kind of different answers, but the end result of, you know, my graph is still kind of looking the same. And I'm kind of surprised by that, to be honest with you. I kind of thought it would be a little bit more interesting than this. What if I started at 300? Still didn't really change. What if I started at 3,000? Notice it, like it sort of still stayed down at the bottom in the sense that, but now it tops out at a totally higher number. So it's like it wants to stay, kind of wants to stay the same, sort of the same general graph. You know, I wonder why that is. Now we're getting something interesting. Notice it kind of went off negatively now. It's like I started at a negative number and then it went off negatively. And so what if I just made it -1? So it's kind of fun because you can play around with different starting. And this is what's really powerful about this is, think of this as like, this is kind of if any of you have read Chaos Theory or the butterfly effect, that kind of a thing. It's kind of like the butterfly effect is the idea that just because a butterfly flapped its wings, that added a little bit of wind to that particular area, which ended up kind of making a big difference. I mean, it wasn't all on the butterfly, but it's just like a tiny difference in the beginning. We started at 0, 1, and we got, you know, one answer with an initial slope of 2. You know, this is what we originally started with. But then if we say, no, you actually started with a negative number, now all of a sudden it's like, oh, now that's kind of cool. So that was actually the first one that I just found randomly, if you will, that was suddenly kind of a neat graph. The rest of them were sort of plain. And so now I find myself thinking, okay, now I'm on to something. Let's play around with that. What if it was -2? Oh, wow, this is such a radical difference. I mean, isn't that crazy? It's like just based on where I started it. So then what if it was like -1.2? Does that get, wow, that's kind of fun. Of course, the trend line, is not working very good anymore, but notice it's the same exact problem. This is the same exact problem. The only thing I changed is instead of starting at 1, you started at negative 1.2, and now all of a sudden we just got this crazy different graph. So, and it's kind of a fun one. And notice kind of what made it, one of the things I want you to notice about this too, is that one of the reasons this happened is because, do you see what the y-axis is? Notice how it's not like 20,000 anymore. When those numbers are really big, like 3,000, then you lose all of this interesting motion, if you will. And so basically by just picking kind of the right numbers here, notice my X's and Y's, really my Y's stayed reasonable. They didn't go off to 1,000. As soon as that happens, whatever cool part of your graph exists, you won't be able to see the interesting. In the beginning, it might be doing this, but if it's doing this with really low numbers, then you're not going to see any of that. And so in a sense, I got lucky, but this is true of almost any one of them. So play around with that, find some cool equation. But interestingly, it's not so much about the equation, it's actually more about where you start. So this is a really good example of the butterfly effect in chaos theory. One person starts here, one person starts here, and yet they have 2 radically different outcomes at time 4. Notice this one ends at what we said, 74 or something like that. But then when we went in here and made it negative 1.2, which isn't that much of a difference, now all of a sudden, look where it ends, negative 3. It's like that's a radical finish as a result of just where that started. And so that's kind of fun. Okay, so I'm going to save those Excel sheets and post them. I'm going to save with the notes I wrote and my explanation. The only other thing I want to quickly say is this, just for those of you that are thinking ahead, just because this is next week. So let me just pull up one thing here. So on the syllabus, it says 5.4, which is Monday, is a worksheet. So it's like, well, where's that worksheet? Well, if you have a book, you haven't looked in here, but if you have a book, early on in the class for homework, there was, this is where I'm posting all the homework solutions and so forth. But there was this homework scans from the 8th edition. If you have a book, you didn't go here because you have the 8th edition, you don't need to go there. But if you click in there, all the pages that they were assigned are here. But when you get down to 5.4, because that wasn't a page in the book, there is the worksheet. So I'll say that again, but I know some of you some of you are kind of working ahead sometimes. So FYI, and basically that's because just like today's assignment was a little too dull, given we live in technology land, the book assignment was way too dull here. And these are really cool examples. And so this is awesome. I can't wait to show this to you. But that's one day.